Hello everyone, welcome to UN Digital class. So in today's class of computer organization, we will discuss about the instruction hazards, and the condition is our conditional branches. That means due to the conditional branches, how the instruction hazards will be taken place, and if the conditional branches are present in a program, then how it will reduce an instruction hazard. And in the previous lecture, we have discussed about the unconditional branches, and due to unconditional branches, how the instruction hazards are happened. And in that we have set a queue, and we use the concept of prefetching also. So in today's lecture, we will discuss about instruction hazards due to the conditional branch presence in the programming. So let's go to the slides. What do you mean by conditional branches? A conditional branch instruction introduces the added hazards caused by the dependency of the branch condition on the result of a preceding instructions. That means when a conditional branch statement is introduced in a program, or you can say that the program is a set of instructions. So in that set of instruction, if there is an instruction which satisfies the branch statements, or it is the conditional branch instruction, then the hazard is caused by the dependency of the branch condition, because whatever the condition due to which, that means if the condition stays true, that means the branch will happen. So in that type of situation, if the branch condition depends on the result of the another instruction, that is preceding instruction, then the hazard will be occurred. And then the decision to branch cannot be made until the execution of that instruction has been completed. That means as the branch condition is depends on the another instruction which has to be executed before that branch instruction, at that condition, or you can say at that type of point, the decision has to make that the branch statement will be executed or not. That means the branch statements cannot be executed until the execution of that instruction, and that instruction means the instruction which, or you can say the output of that instruction which affects the branch condition, or in other words you can say the instruction whose execution or you can say the result of that instruction is depends, or it hampers the branch conditions. And then branch instructions represent about 20% of the dynamic instruction count of most programs. So in most of the programs, whatever the programming language we have used, the branch instructions are all about the 20% of the all of the instructions of a program. Then let's see what do you mean by delayed branch. So the instructions in the delay slots are always fetched, therefore we would like to arrange for them to be fully executed whether or not the branch is taken. That means if there is an instruction in the delay slots, that means that delay slots or that instructions has to be fetched so that the delay will be minimized, or you can say the delay slots or the instructions which are present in that slots, they has to be or they has to be arranged in such a way that the instructions has to be executed whether or not the branch is taken. Then the objective is to place useful instructions in that slots. And as we have discussed that there is some instructions which are present in the delay slots, that instructions will be executed if the branch instruction is satisfied or not. Okay, that means it does not depends on the branch conditions. So in that type of situations, some useful instructions, or you can say the most priority instructions has to be placed in that type of slots, so that the execution of that instructions are not depends on the execution of the branch statements. Then the effectiveness of the delayed branch approach depends on how often it is possible to reorder the instructions. That means we cannot place all the instructions in that slot. So how will increase the effectiveness of the delayed branch? That how the reorder instruction will be possible. That means we cannot reorder all the instructions formats. So, okay. So, we have to arrange the instructions in such a way that which is possible, so that the processor can execute the instructions in a sequential manner. Then this is the example. So, it is the original program loop and it is the concept, it is the instructions after reordering the instructions. So, here you can see the loop, that means shift left y shift 1, then decrement R2, then if the branch is equals to 0, that means if the condition is true, then it will go for the loop level, that means here, then it will executed in a circular manner until this condition stays false. So, then after condition false, then it will come out of the loop and then it will execute this instruction, that means add R1 with R3. That means the execution of this instruction is basically depends on the output of this, okay, and this statement is inside the branch. So, here you can see after reordering the instruction, that means first it will decrement the R2, then branch if 0, then loop, okay, then when it is loop, that means loop is here. So, again it will decrement R2, then branch equals to 0, then loop, like this. That means this instruction is not included, or this is not depends on the condition of the branch. That means whether the branch condition is true or false, these statements will be executed, okay. But here the this instruction will be executed after the branch will be false and it will be come out from the loop. So, here you can see the after reordering the instructions, the shift left instruction is here. So, whatever the value in the R1, here in this next instruction we can use it, because here you can see here it is our source operand, okay, and here is your destination. That means after adding the content of R1 with the R3, then we have to place the result in the R3, and as R1 is the source operand, so we have to collect that from the processor registers, and here R1 is our destination register. So, these instructions execution depends on this instructions execution, okay. So, in this type of condition, that means due to the branch, the execution of this instruction delayed for some period of time, okay. So, we reorder these instructions so that this instruction which is in the slot and that is depends on the branch instruction previously, but now after reordering, this instruction execution is not depends on the condition of the branch, whether the branch is true or false, this instruction will be executed. And then this is the diagrammatical representation. Here you can say that decrement instruction, then branch instruction, then shift delay slots. So, in the delay slots, the shift instruction is written. So, here it is occurred, then decrement if the branch taken, then branch, then shift, like this. So, this will be the loop like structures, and here you can see the execution of the instruction is in a sequential way. So, that means there is no delay, okay. And then you can see the next one is our branch predictions. So, to predict whether or not a particular branch will be taken. So, if the instruction hazards occurs due to the presence of a conditional branch, and then how we will solve that, or how we will avoid that instruction hazards, that is our branch predictions. That means we have to predict whether a particular branch will be taken or not, and simplest form is that assume that branch will not take place and continue to fetch instructions in sequential address order. So, what this branch prediction concept says that you have to assume that the branch is not takes place, so that the processor can fetch the instructions in a sequential manner, because we know that when a branch statement occurs, at that point of time the PC is incremented to the branch target address, okay. But in a sequential manner or in other executions, PC will increment according to the next instructions address, means either by 4 or by A depends on the addressability, and then if the branch instruction occurs, then the PC has to be incremented, or PC has to contain the branch target address as the next instruction's address, so that the processor can collect or it can fetch whatever the instruction is placed on that location. So, we have to assume that branch will not taken place, and the instructions whatever written, they has to be executed in a sequential manner. Then until the branch is evaluated, instructions execution along the predicted path must be done on a speculative basis. So, until the branch is evaluated, that means until the branch condition is satisfied, or you can say until the branch instruction is executed, the instructions are executed in a sequential manner. Then speculative execution means instructions are executed before the processor is certain that they are in the correct execution sequence. That means that is the imaginary concept that the instructions are executed before the processor, and it is certain that they are in the correct execution sequence. Whatever we assume that there is no branch, or the branch will not taken, and the instructions are in a current execution sequence. Then need to be careful so that no processor registers or memory locations are updated until it is confirmed that these instructions should be indeed be executed. So, we have to careful that no processor registers or any type of memory location are updated until it is confirmed. That means whether the branch will take place or not, if that is confirmed, and the instructions should have to be executed, and then at that point of time no processor registers or the memory locations we cannot update. And then here you can see, if we will predict the branch incorrectly, then what will happen? Here you can see the instruction I1 is about to compare, and this instruction will take 4 clock cycle, and here we assume that the pipeline contains 4 stages: fetch, decode, execution and write. And then here you can see the branch is greater than 0. So, we have to predict that if the branch will be taken place or not. So, we are predicted that the branch is not takes place. Then F2, here the branch statement is fetched, and then decode, then here is our P2, and then execution will happen. But as it is a branch instruction, is it not taken but it is executed, then whatever the instruction will be followed to that branch instruction, that will be stalled. Okay. So, if we will incorrectly predict the branch, this will happen. That means we cannot execute the instructions in a sequential manner, or whatever the instruction which will followed by this branch instruction, that instructions execution has to be stopped, or it is halted or stalled, you can say, for some period of time or till the execution of the branch, because we have predicted incorrectly that the branch is not taken. So, if incorrectly predicted branch is happen, then this will be the case. Then next, better performance can be achieved if we arrange for some branch instructions to be predicted as taken and others as not taken. Because in the previous example we have seen that if we will predict that branch will not taken and we are executing the instruction sequentially, then there may be some cases that the instructions which is after the branch instruction may be stalled. So, better to assume that some branch instructions are taken and some are not taken. So, use hardware to observe whether the target address is lower or higher than that of branch instructions. Okay. So, there must be a hardware circuit which will calculate the target address, that means whether the target address is lower or higher than the branch instructions address. Then let compiler include a branch prediction bit. That means in that circuitry manner, the compiler has to insert or it has to include a bit which will used to set whether the branch prediction is takes place or not. If the branch prediction were taken, then that bit will be set to 1. And then so far the branch prediction decision is always the same every time a given instruction is executed, that is called as our static branch predictions. Then okay, so that means if the branch prediction decisions are always same, whatever the instructions we are executing, that means that is called as the static branch prediction. So we have discussed that the static branch prediction means the branch prediction decisions is always the same every time a given instruction is executed. That means in this previous example we have discussed that in this, that if the incorrectly predicted branch will takes place, then the branch prediction is takes place in the cycle 3, and while instruction I3 is being fetched, here you can see the fetch unit predicts that the branch will not be taken, and it continues the fetch instruction I4 and I3, and you can see here it will fetch the instruction I4 as I3 and enters the decode stage, and as the I3 enters into its decode stage, then the I4 instruction will be fetched, because we know according to the pipelining, if one instruction is in the decode phase, then if the next instruction is not depends on the result of that decode fetch, then that instruction can be fetched by the fetch unit, and then the result of the compare operation, are available at the end of clock cycle 3. So assuming that they are forwarding immediately to the instruction fetch unit, the branch prediction is evaluated in this clock cycle 4, because after execution of that branch instruction, whether the branch condition is true or false, that will be calculated. So the result will be comes in this 4th clock cycle, and at this point the instruction fetch unit realizes that the prediction was incorrect, because previously we have predicted that the branch is takes place. That is why the fetch unit already fetched this I3 instruction, and also the I3 instruction is going for its decode fetch, and here also the I4 instruction is already fetched. That means these two instructions are wrongly fetched, as we predict that the branch will not take place, and the processor executes all the instructions in a sequential manner. So the two instructions in the execution pipe are stalled, and then a new instruction IK is fetched from the branch target address in the clock cycle 5, because if the branch condition is true, that means the branch will be take place, and after the branch condition will be satisfied, the processor has to execute whatever the instruction is present in the branch target address, and that branch target address is calculated in this clock cycle 4. So after calculating what is the instruction which is contained by the branch target address, let that instruction is our IK. So in the 4th clock cycle, or the branch target address is calculated, and then in the 5th clock cycle the instruction IK will be fetched. But these two instructions which are wrongly fetched by predicting that the branch is not take place, so that execution will be stopped. And then you can see, however, that we have already discussed that to achieve the better performance, we arrange some branch instruction to be predicted as taken and other as not taken, because if we will predict that all the branch will not taken, then the condition of this instruction will be happen. So we have to consider that branch instruction, or you can say some branch instruction to be predicted as taken and some are as not taken. So this is all about the today class. So in today class we have discussed that the instruction hazards is takes place, or you can say the delay in the pipeline is takes place due to the presence of branch conditions. And what are the solution? We have to predict that the branch will not taken, and if in all the conditions if we will predict that branch will not taken, then there is arise some problems. So we have to assume some branches has to be taken and some branches will be not taken. So in that conditions, and there must be some cases that the prediction decisions will not be changed. Okay, so that is called as our static branch predictions. So this is all about our today class. In the next class, we will discuss about some new concept of the computer organization. Till then, keep watching. Thank you.